Hello, and welcome back to College Algebra Notes. We're on Outcome 5, so this is the notes for the fifth homework assignment. This section we're going to solve some equations. These will all be linear equations, which we've kind of seen already with the linear functions, but now these are just equations. You'll notice that these only have one variable kind per problem. And then we'll see a few applications, and that's about it for this section. So they're just mostly solving equations, figuring out what x is kind of thing. So first, again, we're dealing with linear equations. These are the things where we have like mx plus b. You notice the x doesn't have a power. It's not squared or cubed or anything, so it's just a plain x. It might be multiplied, might be added. There might be multiple x's, something on both sides, but you won't have any powers or anything like that. So that's why we're just going to call these plain linear equations. So the first one, stuff like this, you probably have seen before if you took a intermediate algebra, or if you took algebra in high school and all that. This should be fairly familiar. Remember that when you have parentheses in an equation, we can't deal much with the stuff inside those parentheses. I can't get rid of this minus 2 or work on getting x by itself, so we always want to distribute to get rid of the parentheses. So the first thing we're going to do is we're going to distribute this 5 through, distribute that to both parts. Anytime we have multiplication outside the parentheses, we can do that. And that will get rid of the parentheses for us. Instead of having 5 times the parentheses, we'll have 5 times x, and 5 times 2, which gives us 10. And that just gets rid of the parentheses. Now we have an equation with x's on both sides. So we want to get all the x's on the same side. So what we're going to do is we're going to subtract the 3x from both sides. Subtract 3x, because that will get rid of the 3x on this side. So that's going to put all the x's on the left side. So this other stuff, the 10s and the 2, we want to get on the right side, so we can work on the x by itself. So I'm going to go ahead and add 10 to both sides. Add 10 to both sides. And I'm doing everything to both sides, because remember with an equation, I always think of an equation like a balance scale. The two sides have to be balanced. They have to be equal. They start off equal. I have to keep them equal. So if I add 10 to one side, I have to definitely add 10 to both sides. So that's a big rule with these equations. If you're going to do something like add 10, you have to do it to both sides. So I've managed to cancel the middle parts. I'm left with 5x minus 3x, which is 2x. Bring down my equals. And 2 plus 10, which is 12. Last step here, I want to undo multiplication. When I have that 2 next to the x, it means multiplication. You always undo multiplication by dividing. So I'm going to divide both sides by 2. Divide by 2, because that will cancel that multiplication with division. We just get x by itself, and 12 divided by 2 gives me 6. So that's the answer we're looking for on this one. This 6 is the number that would make this true. Remember, when you solve an equation, you're always finding a value. If you plug it in for that x, it would make it true. If I do 6 minus 2, I get 4. Times 4 is 20. If I do 6 times 3, I get 18. 18 plus 2 gives me 20. And 20 is equal to 20. With 2 both sides give me 20. So that's true. So 6 is a valid answer. So that's the idea here. When we solve an equation like this, we're always looking for the number that we can plug back in for x and make sure it works. Okay, let's try one more. This one, notice there's fractions in this equation. I wanted to show you this trick. Hopefully it's a reminder. You've hopefully seen it before, but if you haven't, I want to make sure I introduce it now. There's a big trick where you can get rid of all the fractions in an equation. If you have an equation with an equals, you can get rid of all the fractions in the equation if you just multiply by a big enough number. And the number that's going to multiply by, that's going to be big enough, is the LCD. Remember, LCD means the least common denominator. So it's the smallest number that all the denominators, all the bottom, so the fractions goes into. In this case, the LCD would be 6, because 2 and 3 go into 6, and that's the smallest number that they both fit into and divide into. So I'm going to multiply everything here by 6. I'm going to distribute that 6 through. I'm going to multiply it through. I'm going to multiply it to this x over here first. And when I multiply, I could do 6 times x, get 6x, and have that over 2. And then I could do the division, 6 divided by 2, and I end up with a 3 left over and the x left over. Or you can think about that when you're going to multiply, you're going to multiply by 6, and 2 will come out of the 6, leaving behind a 3. If you think about the fact that 6 is 2 times 3, so it's made up of a 2 and a 3, you can kind of think about canceling as you multiply. And I like to do this usually. I usually try and cancel as I multiply and think, okay, 6, cancel the 2 part out of it, and then we just left with multiplying the 3 part. The next one, when I go to multiply this 6 times this x by itself, there is no fraction bottom, so there's nothing to cancel, so I'm just going to do 6 times x. So that one just gives me 6x. Nothing to worry about canceling because there's nothing on the bottom. When I go to do the next one, on the other side of the equals, when I multiply 6 times this part, over your equal sign, this 6 and the 3, those will cancel. So we're going to cancel the 3 part out of that 6 and just leave behind a 2. So the x minus 1 on the top is going to get multiplied by 2. So I'm going to have 2 times x minus 1. Again, I could multiply 6 through here first and then divide the 3 out, but I might as well just cancel the 3 in the first place and just multiply by the 2. Okay, so I got rid of the fractions. And this is my big trick. I use this all the time. We'll see this throughout the semester. Anytime we have fractions in an equation, we'll just multiply by a big number that will get rid of all those fractions. If you want, you could multiply once by 2 and then once by 3, and that would give you the same result. The 2 would cancel with this, 3 would cancel that, and it all ended up basically being the same. But I usually just try to find the LCD and multiply by that big number right off the bat just to get rid of it all in one step. Okay, so now we're back to solving an equation with parentheses. So we're going to distribute 2 times x is 2x, 2 times 1 is 2. So we got all that stuff. We got rid of the parentheses. Again, we're back to trying to get all the x's on the same side. We also have 2 x's on this side, so we can actually first off combine these x's. If they're on the same side, remember you can always combine like terms. 3x plus 6x is 9x. Now I'm going to go ahead and subtract that 2x on both sides. Just get rid of this 2x. Trying to get all these x's together on the same side. 9 minus 2 gives me 7x equals negative 2. Here I want to get rid of the 7, so I'm going to divide both sides by 7. Divide by 7 on both sides. Get rid of this guy. I'm undoing multiplication with division. So my final answer for this one is x equals negative 2 sevenths. And it's okay to get fractions when you're solving an equation like this. That's fine. That's definitely possible. When you type in my math, you just type this a fraction with a negative in front of the fraction. That would be your answer. So, a lot of times when you solve equations with fractions in them, your answer does tend to be a fraction. It's not a rule. Sometimes you get a whole number, but that's kind of a good sign. It's kind of a typical thing to see. So I'm not very surprised when I have fractions in my equation. My answer is a fraction. Okay. I'll try a couple more. These ones are special though, and you'll see why as we solve them. So again, I've got parentheses here, so again I'm going to distribute, just like before. I'll distribute both of these, just to get rid of those parentheses. 3 times 2 gives me 6x, 3 times 8 gives me 24. We have the minus. 2 times 3 gives me 6x, 2 times 2 gives me 4. We have the plus. And then what happens here is we want to get rid of the 6x on the right side, so I'm going to go ahead and subtract 6x. When I do that, when I subtract 6x on this one, I end up with the 6x canceling on both sides. All my 6x, on both sides cancel, so I'm left with just the negative 24 on this side and the positive 4 on this side, and the x's are gone. And this can happen. You can get an equation when you go to solve it, the x's all go away, and you're left with an equation that is, in this case, false, right? Because negative 24 is not equal to 4. And what this tells me is that there is no value that makes this expression work. And it said on the first page, if you're paying close attention, it says that equations typically have one solution, but can have no solutions, or it can actually be true for all real numbers. So those all three can happen. You can write an equation where it's only got one answer. You can write an equation that has no answers. And this is one of them. If you notice, after we distributed, we had 6x minus 24 is equal to 6x plus 24. Well, you can't take 6x, whatever that is, because it should be a number, and subtract 24 and add 24 and get the same value. That's just not possible, and that's why this is false. No matter what you put in for x, you're not going to get the same answer. So this is false. There is no solutions. So this one has no solutions. It's false. You can't get an answer for this. And that's possible to write equations like that. You don't see a lot of them. Most of the time people try not to write equations with no answers. But there are sometimes some equations you can write and they just don't have a solution. Let's try one more. Here you'll notice we have the fractions again. So again, I want to multiply by that LCD because that's my big trick. If I have fractions like this, I like to multiply by the LCD and get rid of all the fractions. So in this case, I look at all these numbers here. I have 2, 5, 15, 10. Well, 2 doesn't go into 15s. I got to go bigger. 30 works, right, in this case, because 2 goes into 30, 5 goes into 30, 15 goes into 30, and 10 goes into 30. So the LCD in this case is actually 30. So I'm going to think about the fact that 30 is 2 times 15, right? That's one way to think about 30. Another way to think about 30 is it's 5 times 6. Another way to think about 30. The last way to think about 30 is that it's 3 times 10. And that'll just help me when I go to do my canceling. I can see the things that make up 30. So if I go and I multiply all this by 30, again, I'm going to distribute. I'm going to multiply it to all these parts. But each time as I go, instead of multiplying 30 times 7 and getting a huge number, I'm going to cancel the 2 part out first. I'm going to look at the fact that 30 is 2 times 15, cancel the 2 part out, and only multiply the 7 by the 15 that's left. I'm going to cancel the 2 part and multiply 7 times 15. Instead of multiplying by the whole 30 all at once and then dividing by 2, I'm going to divide the 2 out first and do 7 times 15. So I'm going to have 15 times that, 7x. And then I do the next one, I do 30 times this one. Well, now the 5 is going to cancel. So I'm going to do 7 times 6, because the 5 is canceled. And I'm just multiplying by the 6 that's left over. So I get 6 times 7. Next one, I'm going to do 30 times this one. Well, now the 15 is going to cancel. So that 15 cancels. I'm only going to multiply the 21 times 2. So I'm going to do 2 times 21. Last step, 30 times this one. Well, now the 10 part cancels, right? The 10 cancels. So it'd be 35x times 3. So it's going to be 3 times 35. I did parentheses this time. It just means multiplication. I could have done a dot again. I should have, but oh well. All right, so but that idea here is when I multiply by that big LCD, all the fractions go away because we can cancel those. And I did it ahead of time, which I kind of want you to practice because you'll see this pop up later on this semester. That's an important thing to be able to do. So that's why I'm practicing it. But you could multiply everything by 30 first and then divide by the bottom, and you get the same answer. But it's a good habit to kind of cancel as you multiply. It saves you a lot of big numbers and stuff too anyways. Because I'm going to multiply these out. 7 times 15, so that gives me 105, I believe, 105x. 6 times 7 is 42. 2 times 21 is also 42. And 3 times 35, so that gives me 90, and 15, that gives me 105x. We see a similar thing going on here. We see that 105x on both sides. So we're going to go ahead and subtract the 105x, get rid of this side, and it's going to get rid of it on both sides. So we kind of think, okay, well, we know what's going on. Look at that and say, that means that it's no solution again? Well, not this time, because this time when you're done, you're left with 42 equals 42, which is true. This time it's true, not false. And so this time the actual answer is all real numbers work. Anything works, because no matter what you plug in, the x part just goes away and 42 still equals 42. So I don't care what you pick for x. So we'll see that this time. It doesn't really matter what the x is. So this one's true. All real numbers are solutions. So all real numbers will be the solutions. Doesn't matter what you pick any number you want, throw in there, and it works. So make it valid solution. It will solve the problem. So that's the idea. Okay, now dealing with these equations and solving them and stuff leads to kind of the idea about solving these functions. We've already talked about linear functions. Just want to make a point here. We're going to talk about this throughout the rest of the semester, so we want to bring up now, and so kind of get the idea in your head, and hopefully you'll see it later and recognize it. And this is what we call the zeros of functions. So if we take a function, remember that's just an equation. We write it with f of x to tell everybody it's a function. It's an equation with f of x. It's a function. Your input's x, your output is the result on this side. What we say is letter C. If we pick a letter, we like to use C for the zeros. If C is a 0, that means that the output of the function is 0 when the input is C. So that means that if you plug in C for x, this will give you 0 for your output. Another way of thinking of this is the point C0, because you're plugging in C and getting out 0. This tells us this is actually an x-intercept, right? Because remember we said x-intercepts, the y value is 0, and the f of x, remember, you can always think of as y. So this is telling us that you get a result y is 0 when you put in C. So this is actually the x-intercept. So a lot of times if you want to, you can graph a function and look for x-intercepts, and those will also be telling you that that's a 0. So a 0 is another way to think of the x-intercepts. It's what makes the function equal 0. So a 0 is something that makes it equal 0. So if I want to find the 0 of a function, well, what I do, I'm actually going to just set it equal to 0, because I'm looking for the number that makes it equal 0. So if I find x makes it equal 0, I found the 0. So that's what I'm going to do on something like this. So if they give you a function and the function notation asks you to find the 0, they want you to set it equal to 0. Replace that f of x, or you can think of f of x as y again, remember. Replace that with 0 and then solve it. So here I'm just going to add 6 to both sides because I'm trying to work on getting x by itself so I can solve. Give that 6. So we get 6 equals 2x. Divide by 2 to undo that multiplication. I'm going to divide by 2. Get rid of that 2 here. And so we see that we get 3 equals x. So 3 is the 0. That means if I do f of 3, I get 0, and that there's a point 3, 0 on this function. That's a point on this function's graph. If I went and graph this, you type in your calculator graph it, and you get 3, 0. It would be the y-intercept, actually. Or, sorry, not the y, the x-intercept. I said the wrong letter. X-intercept, because y is 0, and this is your x-intercept. Okay, let's do one more. So here you go, another function. Again, if we want to solve this, set it equals 0, so I'm just going to set that equals 0. So 0 equals negative 4 plus 2/3 x. Again, if you don't like fractions and you're really like, oh, yeah, fractions, you can just multiply everything by 3. And that will get rid of the fractions. Remember, that's always a trick. If you have fractions in an equation, multiply by that denominator, and it will get rid of the fractions. So I just do 3 times 0. Well, that's easy. It's still 0. 3 times 4 is 12, so I get negative 12. Plus here, the 3 times the 2/3, well, the 3's cancel. Divide by 3, multiply by 3. Those are opposites. Just end up with 2x. And that's one way to just get rid of fractions. So if you ever want to get rid of fractions, multiply that by that common denominator. When there's only one fraction, that is the common denominator, right? So that makes it easy. Okay, so I want to get x by itself, so I'm going to add the 12 to both sides. Add 12 to both sides, and get rid of this negative 12 here. Just work on getting this 2x by itself. So we get 12 equals 2x. Last step, divide to get rid of this multiplication. So we divide by 2. Get rid of that. And so we get 6 is equal to x, so we get 6 for the 0. So again, if you do, and this is our new function f, if I do f of 6, I get 0. You plug 6 in here, it's going to work. You can check it, right? If you do 6 times 2/3, well, 6 times 2 is 12, divided by 3 is 4, and 4 plus negative 4 will give you 0. So it does work. Again, this tells me that the point 6, 0 is a point for that function. So that's a 0 of a function, just something to deal with. Okay. Now, a couple practical uses, some real-life uses of linear functions. One of them is what we call the distance or motion formula. So the distance formula, pretty straightforward, it just says the distance you travel is equal to the rate times the time. So the distance you travel is equal to the rate r, so that's your speed, and your times t. So if I'm going 60 miles per hour times 2 hours, 60 times 2, I've traveled 120 miles. And that's all this is. Distance is rate times time. So you'll see some problems. This is on your formula sheet again. This distance equals rate times time. So you don't have to memorize it or anything, but you should know how to use it. So if I give you a problem like this one where they say, okay, I want to travel 240 miles, and if you traveled, okay, so Sierra needs to travel 240 miles to a wedding, how long, so we're looking for the time, would it take for if she traveled at 60 miles per hour? And there's actually 2 parts to this question, so let's answer the first part and then we'll go on from there. Okay, so noticing that they asked us, they told us the distance, right, because that's how far you traveled. They asked for time, and they say traveled at 60 miles per hour, that's the rate. So I'm going to just put in what I know here. I know the distance is 240, the rate is 60, and the time is what we don't know. So in this problem, I'm actually going to solve by dividing. You'll notice when you work with this equation, a lot of times you won't divide, sometimes you multiply. It all depends on which value you're looking for. Since I'm looking for time, I divide by 60 on both sides. And that tells me, well, 240 divided by 60 is 4. It's going to take me 4 hours, right? Because we're doing per hour. So this is going to be 4 hours. And that's how long. So that's the first part. That's the answer to the first question. How long would it take you to get the 240 miles? Well, you do it in 4 hours. The second part says how fast. So now I'm actually looking for speed. How fast would you have to travel to get there in 3 hours? So maybe you don't want to wait 4 hours to get there. You want to get there faster. So in this case, we're going to look for the time is 3 hours, so we're going to look for the rate. The wedding's still in the same location, so our distance is still going to be 240. So in this case, we'd still have 240 for our distance, but we're looking for the rate if we want to get there in 3 hours. Now we have the time and are looking for the rate. Well, again, since we're looking for something on this side, we're going to dividing both sides to get that rate. So we're going to divide here to cancel that 3. And 240 divided by 3 gives me 80 equals r. And that makes sense, right? Because originally we said we're traveling 60 miles per hour. It's going to take us 4 hours to get there. Well, now we want to get there faster, so we have to travel faster, right? So 80 makes more sense because we're doing 80 miles per hour. Faster speed is going to get us there quicker. So that Makes sense. That's one thing you always want to do with problems like this. If you're doing a story problem, you'll always stop and, does my answer make sense? Well, if it takes 4 hours at 60 miles an hour, 3 hours is going to be faster. 80 miles per hour makes more sense. Another equation you'll see in this section, it's an important equation to know, is the simple interest formula. So this is the simple interest formula. Interest is, again, when you loan money to someone and then they pay you back, and usually they give you a little bit extra money because you let them borrow the money, so they pay you interest. We're going to do simple interest. We'll talk about the more complex compound interest later on in the semester. But simple interest, use I for simple interest, is based on the principal. Principal for interest is how much you borrowed or loaned. Depends on which side of the arrangement you're on, right? If I loan my friend Joe $5, well, he's borrowing, I'm loaning, and that principal is the $5. That's the original amount loaned. And then we'll use an interest rate R, and so that's how much interest percentage-wise. When you get a 5% loan, that's what they're talking about. The interest rate R is 5%. And then T years, we'll do these typically in years. The formula is the interest equals the principal times the rate times the time. That's your formula. So interest equals principal times rate times time. So you just multiply those two together to find your interest. Okay, so Cliff has invested some money in a savings account. It earns 12% interest. So that's an important thing to know. It's the interest rate, so that's our R. If Cliff invests $500, how much will he have after 1 year? So here they're telling us interest rate R. You invest 500, that's going to be your principal, that's your starting amount. And then the 1 year, that's going to be our time. So if I want to find the interest, that's what we're looking for. How much, we want to need to know the interest. We're going to take the principal, $500, times the rate. Now, when you use rate, you got to be careful because this is 12%. You're not going to put 12 here because if you multiply 500 times 12, you're not going to get 12%. You're going to get 12 times 500. You get a ton of money. So when you use interest rate, you always want to turn them into a decimal before you multiply. So we're going to do 500 times 0.12. And in this case, since it's only doing for 1 year, it's going to be times 1 for the years. So that'll give us our interest. So our interest is going to be 500 times 0.12 times 1. And that'll give us our interest. 500 times 0.12 times 1. And so he gets $60 worth of interest after a year. If he invests that money and it pays interest, he's the one lending it to someone else. Now, you do have to be careful with questions like this because it says how much will he have after 1 year. Well, when you invest money like that, you expect to get it back, right? You don't expect it just to be gone forever. So you'll have $60 in interest, but total, he'll actually have total $560, right? Because he has his original principal plus $60 in interest. So he will have that much at the end because that's his total. So be really careful when we're looking at a question like this. You have to really think about, are they looking for just the interest or are they looking for the total amount that it will have? And then they want to know how much will he have, the whole amount. If they just asked for how much interest will it earn, then we were just given the 60, but they wanted the total. Okay, this one also has a second part. I kind of doubled down on both these questions. Okay, so instead of doing it that way, if instead Cliff has a total of $672, so that's his total at the end of 1 year. So again, he's doing this just for 1 year. How much did he originally invest? Now in this case, we're actually looking for the principal. What was the principal? If his total was $672 and he had 1 year for his time, and we're still going to use that same interest rate because it didn't say anything about changing the interest rate. So we'll use R as 12%. Now this one you got to be careful though, because when they give us the 672, you're probably tempted to sit there and go, oh, so 672, that's your principal. No, because this isn't how much you had at the beginning, it's how much you had at the end. Maybe you're thinking, oh, it's the interest. But this is the total, right? It's not just the original amount he invested, it's the amount he invested plus the interest. So this problem gets a little tricky here because I can't use this as the total, because I don't have a formula that gives total. I can't use it for interest because it has extra money in there. So what I have to do for this problem is I actually have to take my interest rate, my R, and tweak it. Because right now the interest rate isn't giving this whole thing, it's just giving the interest part. But if I take my interest rate and I add a 1 to it, so I add 100% to it. If I take it and I make it 100% plus the 12%, then this is actually going to give me the total. So the difference is if I had just done 12%, I would have just gotten the interest. But if I add in 100%, well, 100% is the whole amount I started with. So it's basically my principal plus my interest. I'm putting them all together because that's how you get total, is you put the principal and interest together. This is a really common trick in business. If ever and whenever you like do markup or stuff like that, where you buy an item for $50 and you want to sell it for 10% markup, this is what people do. They take 100% plus the 10% markup, add together and do that's 110%, and that's what they multiply by to get the newer higher price. So that's what we're doing here. Since this total is both the principal and the interest, we're taking the interest rate, which is the 12%, plus the 100% of it, because that's the original how much we had, all of it, put it together, and that's the interest rate we're going to use. So we're going to use 112% for our interest. And now we can use this number, 672, for our final amount, interest, because we're using 112 for the rate. So we're going to put 672 in for interest, so 672 equals principal is what we're looking for. We don't know what the principal is. That's what we're looking for. Rate, we're going to use 112, but now again, this is a decimal, so we're going to move it over to decimal 2 spots, so it becomes 1.12. You can move that decimal 2 spots since you get 1.12. And again, this is 1 year, so time is 1. And that's going to give us our equation we can solve and find principal. Since 1.12 times 1 doesn't really change anything, we can just call that P times 1.12. Multiplying by 1 doesn't change the number. And to solve this, we're actually going to divide both sides by 1.12. So we're going to divide by 1.12. And that's how we get that principal there. So the principal, 672, divided by 1.12, we get that the original amount was 600. So 600 is the principal. Now sometimes with a problem like this, you might be able to guess and check a little bit. So maybe you could think, okay, well, 672, that's close to 600. Let's guess that's the principal. And you could throw principal 600 in there and do 600 times 12% and see if that gives you the $72 that puts you up to that total of 672. And that's totally fine. I have nothing wrong, no problem against working a problem a little bit backwards, or being creative in your solving problems. I think that's a great idea, a great thing to do. So if you look at a problem like that and you find a different technique, something else that helps you solve it, that's fine. Of course, when it comes to the test, if you're doing a problem like that, you want to make sure you show your work. So I know where you got it. If you say, I thought 600 was the principal, so I guessed it and tried it out to see if it worked, that's fine. That's a totally legitimate method. Okay, last page for this. So we kind of saw some story problems that we solved. So I want to just talk about and introduce this general kind of approach to problem solving. The hard thing with problem solving in math is every problem's a little bit different. So there's not just a way to do it right off the bat. You always know how to do a problem. But there's a good approach to a problem. That's what this goes over, just a little general approach. So first thing you do is you familiarize yourself with the problem. So you go back and you read the problem a few times. You're going to look at it and you're going to read it and read it again. Make sure you understand it. Read it carefully. After you've read it a few times, you think you kind of got an idea what's going on, a little bit at least, draw a diagram. Draw a picture. Draw something that shows you what's going on. You can label ideas. List the things you know. If you have a picture there that's really helpful, you can kind of identify the things on the picture that you know, so you label those. Assign a variable for any unknown, so you're going to use a letter, but make sure you really clearly label it, because if you don't label your unknown, you're not going to know how to use it. So clearly label that. Look up any needed information. Okay, so once you've read through it, drawn your diagram, listed those known quantities, signed your variables, looked up any information, maybe looking at formulas, using your formula sheet, then you should be ready to write an equation. Based on what you know from what you've written down, you'll want to write an equation that you can use to solve the problem. Make sure when you write an equation that if you have more than one unknown, you don't just use lots of letters, lots of different variables. I've seen a lot of times where students will write a problem, write an equation, and it's got X, Y, and Z, all those variables. And then they can't solve the equation because there's too many variables, too many different variables. So if you can, you want to write all unknowns in terms of just one variable. So you're only going to use just one variable. You pick one thing to be, okay, this is my letter X, and then anything else you should be able to kind of relate to that. And be consistent. When you're using your variables, make sure you're always using it for the same thing. That's another big thing. See a lot of students using X for this, and they use X for that, and they use X for something else. And then when you solve, it's like, well, what does X even mean at that point? Because you used it for too many things. Okay, so after you've written an equation, making sure that it makes sense, then you solve the equation, right? And that's the idea of algebra, is to solve these equations. And then go back and make sure you check your solution. Make sure it works. Go back and plug in. Now that you think you know what the value is, does it make sense in the equation? Try and make sure it's a good solution. So check it. And then, of course, you always want to clearly answer. Write down a label. So we'll do one more example just to kind of show all that. But that's the idea. These are just kind of the process. Something you should think about as you're going through, things you should keep in mind. So for this problem, they tell us the perimeter of a swimming pool is 112 meters. So right off the bat, we know the perimeter is 112 meters. They say the length of the pool is 5 meters more than twice the width. So length is 5 meters more than twice the width. And they want to know what are the dimensions. So if I think about what's going on here, again, I'm going to read it carefully. I'm going to go through it. I got a pool. It's 112 meters is the perimeter. I have to talk about the length and the width. And then I draw a picture. And because we talked about length and width in this pool, I'm guessing it's probably going to be a rectangle, right? It could be length and width. They tell us the length is 5 more than the width, so the length would be the long side, the width would be the short side. Have something like that. Now I'm probably not going to use two different variables, right? Because again, if I use two different variables, I'm going to kind of be stuck. So I'm going to look for one of these. Maybe I'll look for just width or just length. But so let's call it W. We'll say that's the width. So the width of the pool. Now, like I said before, if you can, write your other unknowns in terms of your variable. So we can look at length and say, well, we know something about length. We know the length is 5 more than twice the width. So the length we can say is going to be 5 more than, well, the 5 more, that just means you're adding 5 to it, twice the width. So 2 times the width. So now we have this length written in terms of the width. So we have a way to think about the length using just the variable W. So now we can just use W the whole time. W for the width and 5 plus 2W for the length. Now we need an equation. Where are we going to get our equation from? Well, we're going to get it from a formula. If you remember, there's a formula for perimeter, and the formula of perimeter is equal to twice the length plus twice the width, because the perimeter of a formula of a rectangle is just both lengths plus both widths. Put those together. So now using the perimeter, 112 they gave us, W will leave as W, and then L, length, we can replace with this 5 plus 2W. We can use this formula. So perimeter is 112. 2 times the length, we're going to replace with 5 plus 2W, because that's the length, plus 2W for the width. And now we have an equation that just has W's, and we can solve that to find out what W is. That's kind of the process. We had to come up with a label for our unknown. We had to kind of write our other unknowns in terms of that unknown. A picture helped us get that. Think about what the values that were given, what they mean. Perimeter is the whole way around the rectangle. We had to look up a little formula. If you haven't memorized, that's great, but if not, you might have to Google real quick what's the perimeter of a rectangle, and you'll find this formula. Okay, let's go ahead and solve this. So to solve it, because there's parentheses, we're going to distribute out parentheses. So 2 times 5 is 10. Then 2 is 4, so we get 4W, still plus 2W, and it still equals 112. You can combine some like terms. 4 plus 2 gives us 6W. I'm going to go ahead and get rid of this 10, because we're going to want the W by itself eventually. So let's subtract 10 across, just to get rid of this 10. So 112 minus 10 gives me 102. 4 plus 2 is 6W. So I got 102 equals 6W, and then divide by 6. To get rid of that multiplication, we're going to divide. So we take 102 divided by 6, whatever that is. Cheat, to pull out my calculator. It's not cheat, but I don't want to do that in my head, so I use my calculator, and we find out that the W, the width, is 17. Then, like I said, once you get an answer, you go back, make sure it makes sense. If we think the width is 17, what's the length going to be? And then what's the perimeter going to be? Well, first off, the length is 2 times the width plus 5. So I could just take 5 plus 2 times 17. 2 times 17 is 34, plus 5 gives us 39. So we know the length should be 39. So if I can take 2 lengths plus 2 widths, I should get my 112 perimeter. So if I do 2 times my length, 2 times 39, plus 2 times the width, 17, that should give me 112. So it works. It makes sense. This is valid. We do get 112 if I do 2 39s and 2 17s, the whole perimeter. So that's the idea. We solve means very problems. You always want to think through all those steps and kind of, you know, think about what the problem's saying. Try and draw a picture that goes with the problem. Think about what you do know, what variables you might need to use. Look up some formulas if you need them. Again, I'll give you questions on tests and stuff where you don't need a formula or the formula will be provided. I'm not going to expect you to have a whole bunch of geometry and other math formulas just sitting around just to use for everything, because I know times after a class we might forget some of those formulas and stuff. There are of course the formulas on the formula sheet, and I will expect you to be able to use those because those are provided. So if I want to use a formula, I'll probably do one off the formula sheet. But that's it for outcome 5. So outcome 5 was really just solving equations. We did talk about some story problems here at the end, but the main thing was knowing what the zeros of a function are, how to find those, and then solving these linear equations. Noticing sometimes you don't have any solutions, sometimes you have infinite solutions, and then of course the regular ones where you just have one solution. So that's outcome 5. So we're done with that, and we'll go ahead and move on, and we'll see you on the next one.